Hi there, so welcome to today's class. I'll continue from where we stopped the very last class, the part 2 of simple AC circuits. So yes, I remember the very last class we discussed, and then we said out that capacitive reactance, which is XC, is 1 over 2 pi FC, and inductive reactance, which is XL, is 2 pi FL. Then I made it clear that F is the frequency, okay, is the frequency, and L is the inductance of the inductor. So you see that frequency is measured in hertz, inductance is measured in Henry, and C is the capacitance, okay, capacitance, and then down is measured in farad. So we have all this. And so remember that I said omega is 2 pi f, so that means we can rightly write this as 1 over omega c, and we can also write this as omega l. So these are very, very fundamental things for us not to forget. So yeah, we now move from there. We spoke about the different types of combination we can have. So we can have the RLC, we said we can have the RL, so we can have the RC, so you can have the LC combination. So and I remember that we saw the RLC combination. Okay, I'll just draw the 4 again. For RL combination, for instance, you have the resistor, and you have the inductor. Sorry about that. You have the resistor and then you have the inductor together. So the resistor is down that looks like a shaft, like something like a shaft, while the inductor is down that looks like a coil. So this is a resistor, while this is the inductor. So we have the two of them connected to an AC source, obviously. Okay, so so this is an RL circuit. Also, we can have an RC circuit, where you have the resistor, and then the capacitor. So this is a capacitor. So this is a resistor, this is a capacitor. You have two of them together, obviously connected to an AC source. Okay, so you have that, and then we can also have the RLC. The RLC, that's the 3 together. That means you have the resistor, you have the inductor, and then you have the capacitor. Okay, so and everything is connected to an AC source, obviously. Okay, so and don't forget that they're always connected in series, just like as you can see. So this is a resistor, inductor, and capacitor. And also I mentioned that you can have an LC, where you have just the inductor and then the capacitor together. Is an LC, okay, and then connected to an AC source, obviously. Okay, so everything connected in series. Okay, so you can have all this. So and I remember that the very last time I mentioned something that we should all take note of this. That there's this particular, I drew this and I said you should take note of it because it's going to help you a lot. So I call this place the R. So you call this place the XL and call this place the XC. So and this is where we are going to be starting today, because the part 2 here today we want to talk about impedance. So I want to look at what really impedance is, and if this structure we have on the board helps us to understand what impedance is. So you don't have to cram the formulas, all those long formulas in textbooks that you see that they talk about impedance. You don't have to cram them. Just note and learn this this diagram, and that's all. So now I would like to define what impedance is before I go into that diagram. So what is impedance? Okay, so impedance, this is the total, alright, or let's say the sum total opposition to flow of current, okay, offered by the various, right, components, okay, multiplied by various components together. Let me just put it that way. So now this is like we taking, okay, you know that for a resistor, obviously the opposition to flow of current is called resistance, isn't it? Resistance, okay. While that one of an inductor is called inductive reactance, okay, inductive reactance, and that one of a capacitor is called capacitive reactance, okay. So now when we have a circuit, okay, together, let's say in a circuit, you get, so not just a circuit, in an AC circuit actually. So let's put it down in an AC circuit. So now let's say you have let's say a capacitor and a resistor together now, and then they both have opposition to flow of current. So I want to look at what is the sum total of the opposition to flow of current offered by two of them. Then we talk about impedance. So impedance is usually denoted as Z, okay. So that's impedance Z. So today we want to look at the different types of circuits and their impedance, okay, or let me say their impedances if that works, okay. So now I will draw that diagram again. So this diagram is a constant diagram that we'll use for all the four circuits. So this is, so now I want to do something. So I'll just call this place, this long one, I call it R, right? So but from this node here, this node where these lines join up here to this junction, okay, is what we call the XL, while from this node down here, okay, is what we call the XC. So it makes sense that way. So now you see that these quantities are actually vector quantities, okay, so we are going to treat them as such. So now to look for the total sum of the opposition offered, right, to flow of current by each of those components, all we just need to do is to take the resultant, right? Okay, so now it depends on which one you are considering. So now, for instance, let's say we are looking at an RL circuit, for instance. So this is R, all right. This straight line here is the R, while this is the L, which is the inductance. Okay, so the inductance. So all we just need to do is we want to take the total sum of the inductive reactance and the resistance. So looking at that, I can draw it. I can pick out just those two parts that concerns R and L. The two parts that concerns R and L, they are just this. This is XL and this is R. So this is 90 degrees. So to take the total resultant, I just need to take the hypotenuse. You get that? To find the hypotenuse of that right angle triangle. And so that hypotenuse is the Z, which is the impedance. So how do I calculate that? It's very simple. I just use Pythagoras theorem. So Pythagoras theorem tells me that Z squared equals to XL squared plus R squared. So that means Z in itself will be square root of XL squared plus R squared. So this is the total impedance, all right, for what's it called now, an RL circuit. It's as simple as that. So we can from this know that. So if you want to talk about the RC circuit, for instance, for the RC circuit, you see that I just need to take that portion of that diagram that concerns R and C, which is the downward part, something like this, isn't it? So this is R, this is XC. So all I need to do is this is 90 degrees. So all I need to do is to find the resultant, which is the hypotenuse, and so that is the Z. And then so we know that Z squared will be R squared plus XC squared, isn't it? So that means Z will be equals to the square root of R squared plus XC squared. Okay, so it's as simple as that. The square root covers everything though. So it's as simple as that. So that is the impedance, alright, for an RC circuit. Okay, so now here comes the brain teaser. Now what if you have an RLC circuit? Do you want to, like, how do you form a triangle? Okay, because you're actually taking the right angle, isn't it? We are taking the hypotenuse of the right angle triangle. So what do we do here? How do we form how do you get the triangle out of this? It's very simple. You know, we say that we are dealing with vectors, isn't it? And we are treating it as such. So now looking at this straight line, for instance, okay. So looking at this, before I even go to the RLC, let's talk about the LC first. LC. So LC is that we are just going to take this straight line, isn't it? This portion. So we can come down and then I'll draw that diagram again so that it will enable us to understand what we are doing. So this is it. So this is R. Okay, this is XL, and this is XC. So now for an LC, okay, an LC circuit, the only part that concerns the LC circuit is this. Okay, this is the midpoint, and so this is XL, this is XC. So if this is vectorial, don't forget that the sum of what's it called, the total resultant of vectors that are acting on a straight line, right? So is actually if they are in opposite direction, just like these two guys now, they're in opposite direction, definitely it will be XL minus XC, isn't it? So just take the difference between two of them. So that is basically what it is. So the resultant of these two guys is actually XL minus XC. So and that is the impedance. So the impedance is actually XL minus XC. It's as simple as that for an LC circuit. But what about an RLC circuit now? So an RLC circuit, we still have the same diagram. This is R, okay, this is XL, okay, and this is XC. So all we just need to do is we need to combine this XL and XC together into one, so that will make the diagram now look like this. Okay, look at that. It now looks like this is R, but now this is now XL minus XC, just like what we did for the LC circuits, where we found the resultant of the LC circuit. So we are going to find the resultant of LC there and then put it on one together now. So we then find this. So this is 90 degrees. We then find the resultant of everything all together. So which is the Z here. Okay, so the Z obviously will be the hypotenuse. That's Z squared equals to R squared plus. Now XL minus XC is the whole of the other side. So that will be XL minus XC all squared. Alright, so if I should take square root of both sides, Z will be equal to square root of R squared plus XL minus XC all squared. So you see, this is the way they got the formula. So that is the impedance for an RLC circuit. So if they say you should find the impedance, so just look for your R, look for your XL, look for your XC, then insert it on the formula into the formula, and then you have the impedance for an RLC circuit. It's as simple as that. So another thing we can talk about here is actually something known as the power factor. Power factor. So now, what is power factor? Okay, I'm just going to give a brief introduction into that here in this class. Then next class we are going to talk about it very well. So, but I'll just give an introduction. So this is R, okay, this is XL, and this is XC. So what really is power factor now? So power factor is actually the angle. Okay, it is the cos. It is actually denoted as cos phi. Okay, so cos phi is actually what we call the power factor. So what is that phi? So what is this angle phi? That's the question. So power factor is the cos of the angle between the resultant, which is the impedance, and the resistance. So this guy is the phi. Okay, so anytime, so for this other circuit that is down here too, I'll just take this, okay, the resultant Z and resistance R. So this is also the phi here. Alright, so we have that cos phi is the power factor. So we just need to take the cos of this angle, and then we have the power factor for that. Okay, so we are going to talk about that very well in the next class. So next class we are going to be talking about power factor, and we are going to be talking about resonance as well. So hope you understand what we discussed just briefly in this class today. So basically all we just discussed is actually how to find the impedance of different circuits from RC circuits to RL circuits to RLC circuits to LC circuits, and it's very simple. Just using your Pythagoras theorem, you can actually find all the impedance, alright, for any circuit. So after the next video, I'm going to be dropping a video that will be solving quite a number of questions on all these AC circuits. So we're going to be solving questions on the RMS value that we have seen in the first class. We'll be solving questions on this impedance, and also be solving questions on power factor and all. So next class we're going to be looking at all those. See you again in the next video. Thank you very much for your time.